Problem 21, we're going to show that any group of order 5 must be abelian. Remember, in a previous video, we showed that a group of order 4 must be abelian as well. We obviously need to know what a group is, so there's a reminder. We'll be using some of those axioms, and then abelian means that every pair of elements commutes, so AB equals BA, and then the order of a group is just the amount of elements. All right, how are we going to do this? Let's assume that there is a group that exists with 5 elements such that it is non-abelian. Well, that means that we have 2 elements, we'll call them A and B, such that AB does not equal BA. That makes our group, because there's only 5 elements, we have EAB, AB, BA. Playing around with this a little bit, we want to come up with some sort of contradiction. And what we're going to do is we're going to look at this element ABA. ABA must be one of these 5 elements. So what we're going to do is we're going to say, hey, does ABA equal E? Maybe, maybe not. Does it equal A? Maybe, maybe not, etc., etc. And if we can show that ABA equaling one of these 5 elements always leads to a contradiction, then we know that this group can exist. So which element is ABA equal to? Well, let's just do them maybe not in order, but in order of difficulty. If ABA equals A, we'll do this one slowly. Well, then you've seen in previous videos that we can cancel on the same side of the equation, or you can think about this by taking inverses on the appropriate sides. But what we get is that AB has to equal E. But we know AB doesn't equal E, so that this is a contradiction, and each one of these is going to follow suit. So this is a contradiction. So ABA cannot equal A. Now what about ABA equaling AB? Same thing, we can cancel and we get another contradiction, that A equals E and that A equals E. So here what we've done in this first step is that we've handled these cases. So we know that ABA does not equal A, does not equal AB, and does not equal BA. So we have 2 cases left to try. What happens if ABA equals E? Well, in this case, we have 2 separate equations here on both sides. So if ABA equals E, then we can take inverses on the right side. So A inverse must be part of this group. And we know that from the 4th axiom. And we know that A inverse times A has to equal E. So what this shows, and that A inverse has to equal A inverse. So we have AB equals A inverse. But we could have done the same thing on the other side. And that's what this shows us, which then says that BA equals A inverse. And we conclude that both of these sides are equivalent, so AB equals BA. But that's a contradiction because we assumed that for these 2 pair of elements that doesn't hold, right? That was the whole point of our trying to construct a group with 5 elements that's not abelian. This was the exact pair that this didn't hollow for. So we know that ABA cannot equal E. So the only opportunity here is that ABA has to equal B. And if we can find a contradiction that ABA equals B, then we're done, because then we know this group cannot exist. So we're going to assume that ABA equals B. What can we do with this? Well, we can multiply by A on both sides, or on the right-hand side of the equation, and then we get AB A squared equals BA. And if we can show that A squared equals E, which would then make this equation AB equals BA, then we're done, right? Because then we've showed the last opportunity for ABA, which is to equal B, leads to the same contradiction that we saw in the previous step. So how can we show that A squared is going to equal E? We know A squared has to equal something in the group, right? So we're going to do the same idea as before. Well, if A squared equals A, we can cancel on one side or multiply by inverses, and we get a contradiction that A equals E. If A squared equaled AB, we can cancel on the left-hand side, and we get that A equals B, but we assume they're distinct, and then the same thing here. So we only have, for A squared, we only have 2 options left. It either equals E, which we want, or it equals B. So we need to find a contradiction when it equals B. And again, we'll set up 2 sets of equation here. On the left, we say A squared equals B, and then we can just multiply by A on the right-hand side and get A cubed equals BA. But if we had multiplied on the other side, we get A cubed equals AB, And again, we combine these equations and say, hey, BA has to equal AB, but that's a contradiction. Therefore, A squared equals E, and if we go back a step, that's exactly what we need, because then this equation here, which was our last chance for ABA to belong to the group, becomes AB equals BA, which we know is a contradiction. Thanks for watching this video. I hope you enjoyed it. Make sure to subscribe so you don't miss out on future videos. And if you have a question about this problem, or if you'd like to request a solution to a different problem you're working on, let me know in a comment below.